Can you imagine stepping foot on a world orbiting another star within your lifetime? Scientists at Caltech have developed a microscopic sail that could be propelled by lasers to speeds approaching 20% of light speed, fast enough to reach Alpha Centauri in just 20 years. The physics behind this technology seemed impossible just a decade ago. Today, I'll explore how these laser-driven light sails work and why they represent our best shot at interstellar travel. From theoretical concepts to groundbreaking experiments, we'll trace the remarkable journey of how humanity's oldest form of propulsion is being reimagined to potentially carry us to the stars. From Kepler to Caltech, the 400-year journey. The story of light sails begins not with modern technology, but with a remarkable astronomical observation over 4 centuries ago. In 1610, while studying the night sky, Johannes Kepler noticed something peculiar about comets. Their tails always pointed away from the sun, regardless of their direction of travel. This seemingly simple observation led him to an extraordinary hypothesis. In a letter to Galileo Galilei, Kepler proposed that the sun must be exerting some kind of pressure, that sunlight itself might be pushing the comet tails away. This was a revolutionary idea. In an era when the nature of light was still deeply mysterious, Kepler intuited that light might possess physical force, that photons, though massless, could somehow transfer momentum. He even speculated this force might one day be harnessed for travel, writing about ships or sails adapted to the heavenly breezes that might carry explorers through the cosmos. Yet Kepler's insight remained dormant, a seed planted in scientific soil that would take centuries to germinate. The 17th century lacked both the theoretical framework and the experimental capability to confirm whether light truly exerted pressure. For over 200 years, this intriguing hypothesis lay waiting, overshadowed by more immediately practical astronomical questions. The scientific foundation finally began to take shape in the 1860s when James Clerk Maxwell developed his groundbreaking equations of electromagnetism. Maxwell's work mathematically demonstrated that light consists of electromagnetic waves and, crucially, that these waves carry momentum. His equations predicted that when light reflects off a surface, it transfers twice its momentum, providing the first theoretical confirmation of Kepler's observation. Still, the amount of pressure exerted by light is extraordinarily small. Maxwell calculated that sunlight at Earth's distance exerts just 4.7 micropascals, a force so minuscule that if you placed a postage stamp in space, sunlight would take centuries to push it the length of a football field. This seemingly impractical force led many to dismiss light-driven spacecraft as fantasy. Experimental confirmation came in 1900 when Russian physicist Pyotr Lebedev and American researchers Ernest Nichols and Gordon Hull independently measured this tiny force using torsion balances with reflective vanes in vacuum chambers. Their work validated Maxwell's predictions and opened the door to practical applications. The Soviet physicist Friedrich Zander formally proposed solar sailing for spaceflight in 1924. His calculations revealed light pressure's key advantage, persistence. Unlike chemical rockets that burn briefly, light pressure continues indefinitely, allowing gradual acceleration to potentially enormous speeds. Progress moved slowly over the decades. The Soviet Union's Xenomya experiments in the 1970s deployed large reflective films in orbit, demonstrating that ultra-thin reflective structures could function in space. NASA developed several designs, including a half-kilometer square sail for a Halley's Comet mission, though budget constraints repeatedly delayed practical demonstrations. The first real breakthroughs came in 2010. NASA's NanoSail D successfully deployed a 10-square-meter sail in Earth orbit, while the Japanese Aerospace Exploration Agency, JAXA, achieved an even greater milestone with Icaros, the interplanetary kitecraft accelerated by radiation of the sun. This spacecraft deployed a 14-meter diagonal square sail and became the first to demonstrate controlled solar sailing in interplanetary space during its journey to Venus, proving the technology's viability. These missions highlighted a fundamental limitation. Sunlight's diffuse nature produces extremely slow acceleration. Icarus achieved a velocity change of just 400 meters per second over 6 months, impressive for zero fuel consumption, but inadequate for interstellar travel. This limitation prompted a conceptual leap. If natural sunlight provides minimal acceleration, what about concentrated artificial light? By directing powerful lasers at a light sail, the pressure could be thousands or millions of times greater. The concept of laser-driven light sails emerged as a potential solution to the interstellar travel problem. Physicist Robert Forward's calculations in the 1980s suggested gigawatt-power lasers could accelerate small spacecraft to a significant fraction of light speed, potentially enabling missions to nearby star systems within a human lifetime. The concept remained theoretical until advances in laser technology, nanomaterials, and miniaturized electronics began to make such missions increasingly feasible. This convergence of technologies attracted serious attention in 2016, when Russian entrepreneur Yuri Milner established the breakthrough Starshot initiative with $100 million in initial funding. The project aims to develop technology to send gram-scale spacecraft with light sails to Alpha Centauri at 20% of light speed, completing the 4.3 light-year journey in just over 20 years. Central to realizing this vision are experiments at Caltech, where researchers have created nanoscale light sails that function as scientific instruments. These silicon nitride membranes, just 50 nanometers thick, allow scientists to precisely measure the forces exerted by laser light, providing the experimental foundation needed for practical spacecraft. The Caltech work represents the culmination of a 400-year scientific journey from Kepler's initial observation to practical laboratory demonstration. These tiny vibrating membranes are the direct descendants of Kepler's heavenly sails, transformed from philosophical speculation to experimental reality. The historical arc from Kepler to Caltech illustrates a common pattern in scientific progress. Observation leads to theoretical insight, which awaits technological capability to test and apply. Kepler could observe and hypothesize, Maxwell could mathematically prove, and now modern scientists can measure and harness light pressure for practical purposes. This connection across centuries reminds us that scientific progress isn't always linear or predictable. Ideas can lie dormant for generations before emerging as transformative technologies. What seemed like an impractical curiosity, the minute pressure of light, may ultimately provide our best hope for becoming an interstellar species. The microscopic trampoline revolution. At the Kavli Nanoscience Institute at Caltech, a material 700 times thinner than a sheet of paper is demonstrating precisely how light can push matter. This microscopic trampoline, measuring just 40 microns on each side, could be the key that unlocks humanity's path to the stars. The structure itself defies intuition. Imagine something smaller than the width of a human hair, yet capable of withstanding the forces needed for scientific measurement and eventually space travel. This silicon nitride membrane stretches just 50 nanometers thick, so thin that if you were to look at it edge on, you'd need an electron microscope to see it at all. What makes this experimental platform revolutionary is its dual functionality. The membrane serves as both a prototype light sail and a precise scientific instrument. This microscopic square sheet, suspended at its corners by silicon nitride springs, creates what researchers describe as a resonator, a structure that vibrates at specific frequencies when disturbed, much like a finely tuned violin string responding to the slightest touch. When laser light strikes this suspended membrane, something remarkable happens. The photons, despite having no mass, transfer momentum to the material. This causes the membrane to vibrate in measurable ways, allowing scientists to detect exactly how much force the light exerts. It's a breakthrough that transforms centuries of theoretical understanding into tangible, measurable data. The engineering challenge behind creating such a structure is considerable. The material must satisfy two seemingly contradictory requirements. It must be incredibly thin to be responsive to the minute pressure of light, yet strong enough not to immediately disintegrate under that same force. Silicon nitride emerged as the ideal candidate for this application. This ceramic compound exhibits exceptional mechanical properties, maintaining structural integrity even when fabricated into films just tens of nanometers thick. Its tensile strength allows it to withstand the stress of being suspended and the repeated vibrations induced by laser light without breaking. The team achieves geometric precision through electron beam lithography, which creates structures with nanometer scale resolution. The process transforms a silicon wafer coated with silicon nitride into the delicate membrane structure, precisely controlling its dimensions and properties. When researchers first observed the membrane responding to light pressure, the lab erupted in excitement. They were witnessing the direct conversion of light into mechanical motion at a scale never before achieved. The membrane's corners are anchored by silicon nitride springs that work like tiny suspension systems. These springs allow the membrane to move in response to light pressure while maintaining its overall position and shape. When photons strike the reflective surface, they impart momentum that causes the membrane to vibrate in specific, measurable patterns. These vibrations occur in multiple modes, side to side, up and down, and rotational movements, each providing different information about the forces being applied. By using optical techniques to monitor these tiny movements, researchers can measure displacement smaller than the diameter of an atom. This measurement capability represents a scientific breakthrough. The membrane effectively transforms the invisible pressure of photons into mechanical motion that can be observed and analyzed, similar to how a drum's surface reveals sound waves through its vibrations. The implications extend far beyond the laboratory. By understanding exactly how light interacts with these ultra-thin materials, engineers can begin designing full-scale light sails with confidence in their performance. Questions previously answered only through mathematical models can now be tested experimentally. How does the material's reflectivity affect momentum transfer? What happens when the angle of incident light changes? How do different wavelengths interact with various sail materials? These experiments allow researchers to study material behavior under conditions that approximate actual space missions. While scaled down dramatically, the physical principles remain the same. The forces experienced by the 40-micron membrane under laboratory laser light mirror those that would affect a meter-scale light sail propelled by a powerful laser array. The measurement precision achieved with these vibrating membranes is astonishing. Forces as small as a few peckinewtons, equivalent to about 1/1,000,000th the weight of an apple, can be detected. This sensitivity is essential because even though light pressure is minuscule, it's exactly this force that would accumulate over time to accelerate a spacecraft to unprecedented speeds. One of the most promising aspects of this research is its scalability. The physics demonstrated at this microscopic scale can be directly applied to larger structures. The membrane serves as a proof of concept for the underlying principles that would govern light sails of any size. As researchers perfect the membrane's composition and structure, parallel work continues on power delivery systems, spacecraft miniaturization, and navigation techniques. Each element must advance together for light sail technology to become viable for actual missions. What's particularly exciting about Caltech's approach is its transformation of theoretical physics into practical engineering. By creating a platform that both demonstrates and measures light pressure, researchers have bridged the gap between physics textbooks and space mission design. These ultra-sensitive membranes could potentially serve as advanced scientific instruments, detecting minute gravitational variations, measuring radiation pressure, or serving as extraordinarily sensitive microphones for faint signals. For space exploration, the implications are profound. Traditional rocket propulsion fundamentally limits our ability to reach distant targets quickly because of the rocket equation's tyranny. More fuel requires more structural mass, which needs even more fuel. Light sails offer a pathway around this limitation. With no propellant to carry, they can theoretically accelerate continuously as long as they remain in the laser beam's path, reaching velocities that conventional rockets could never achieve, measuring the unmeasurable force detection breakthroughs. The rocket equation creates a fundamental limit for traditional propulsion, but light sails offer a potential workaround if we can accurately measure their effectiveness. Scientists faced an extraordinary challenge. How do you detect and quantify forces so minuscule they operate at the picometer scale, that's trillionths of a meter, yet could theoretically accelerate spacecraft to unprecedented velocities? This measurement challenge represents one of the most significant hurdles in light sail development. For decades, scientists operated largely on theoretical models rather than empirical data, because the forces involved, photons striking reflective surfaces, produce effects almost impossibly small to detect with conventional instruments. Traditional force sensors simply lack the sensitivity required to measure radiation pressure accurately, creating a scientific blind spot that has hindered practical engineering applications. The measurement problem becomes even more complicated when you consider that any instrument sensitive enough to detect these forces would likely be affected by numerous confounding factors: thermal fluctuations, gravitational variations, electromagnetic interference, and even quantum effects could all mask or distort the tiny signal scientists are trying to isolate. Imagine trying to balance a feather on a razor's edge. During an earthquake, that's the level of precision researchers needed to achieve. Caltech's breakthrough approach solved this problem through an elegant dual-purpose design. Rather than treating the light sail and measurement apparatus as separate systems, it integrated them into a single platform. The nanoscale silicon nitride membrane serves simultaneously as both a prototype light sail and an extraordinarily sensitive force detection instrument. To achieve this remarkable sensitivity, the research team built a custom vacuum chamber housing the microscopic sail and incorporated a sophisticated interferometer into their microscope system. This setup allows them to detect movements as small as picometers, a scale so tiny that a single hydrogen atom has a diameter of about 100 picometers, meaning these researchers can measure displacements smaller than atomic dimensions. Interferometers work by splitting light into two paths and then recombining them, creating interference patterns that change with incredibly small movements. When the laser strikes the membrane, causing it to vibrate, these vibrations alter the interference pattern in ways that can be precisely measured. This allows researchers to quantify exactly how much the sail moves when struck by light, essentially measuring the force of light itself. This measurement approach can detect both linear and rotational movements with remarkable precision. When light strikes the sail off-center, it creates a torque that causes the membrane to rotate slightly. The platform measures these rotations precisely, providing critical data about how light sails would behave in space, where maintaining proper orientation relative to the propelling laser beam is essential. The mechanical stiffness of the membrane, how much the springs deform when pushed by the laser's radiation pressure, represents another critical parameter. By carefully measuring the stiffness, researchers can determine exactly how much force the laser exerts on different sail materials and designs. This allows for direct comparisons between theoretical predictions and actual measured performance, bridging the gap between physics equations and engineering reality. Consider the implications of this measurement capability. Engineers can systematically test different materials surface treatments and geometric designs with unprecedented precision. Rather than relying solely on theoretical models or macro-scale approximations, they can directly measure how nanoscale variations affect performance. Does a specific pattern of nanoscale ridges improve reflection efficiency? Does a particular material composition reduce absorption? These questions can now be answered empirically. The research setup's ability to measure side-to-side motion holds particular significance for future light sail applications. In space, a sail that drifts sideways out of a laser beam would lose propulsion. The Caltech platform allows engineers to study these lateral movements and develop self-correcting sail designs that would automatically maintain alignment with the driving laser beam, a critical requirement for any practical interstellar propulsion system. This measurement breakthrough transforms light sail development from a largely theoretical exercise into an evidence-based engineering discipline. Each potential design modification can now be tested, measured, and quantified. The data generated allows for iterative improvements based on empirical results rather than theoretical predictions alone. Scientists can now confidently state the specific force generated by a particular design when struck by a given laser power. The vacuum chamber environment is another essential component of the measurement system. In normal atmospheric conditions, air molecules would interfere with both the sail's movement and the measurement process. By conducting experiments in a vacuum, researchers can isolate the pure effects of light pressure without atmospheric contamination, closely mimicking the conditions a light sail would experience in space. This measurement platform creates a critical feedback loop between theoretical physics and practical engineering. When actual measurements diverge from theoretical predictions, as they inevitably do in cutting-edge research, physicists gain insights about phenomena they hadn't fully accounted for in their models. These insights lead to refined theories, which in turn guide new engineering approaches, accelerating the development cycle. For full-scale light sail development, these measurement capabilities address several critical challenges. Engineers must determine optimal sail thickness, thin enough to minimize mass, but thick enough to maintain structural integrity. They must quantify exactly how different materials reflect versus absorb laser energy, as even minimal absorption could lead to catastrophic heating. They must understand how sail geometry affects stability during acceleration. All these questions can now be addressed with unprecedented precision. The ability to measure picometer scale movements also enables researchers to identify potential failure modes before they become catastrophic, such as detecting resonant vibrations that could cause structural damage. What makes this measurement breakthrough particularly remarkable is that it required solving two extraordinarily difficult problems simultaneously, creating a material thin enough to be demonstrably propelled by light, and developing a system sensitive enough to measure the resulting movement. The Caltech team's success in addressing both challenges represents one of the most significant advancements in light sail technology to date, from stars to planets, shifting mission objectives. As engineers perfected these impossibly sensitive measurements, they discovered something unexpected about light sail potential. The technology designed to reach Alpha Centauri might actually revolutionize exploration much closer to home. This surprising pivot in mission planning has scientists reconsidering the immediate applications of what was once viewed primarily as interstellar technology. When breakthrough Starshot launched with $100 million in initial funding, it aimed to send gram-scale Starship spacecraft to Alpha Centauri at 20% of light speed, completing the 4.3 light-year journey in just over 2 decades instead of tens of thousands of years. Like a rocket engineer designing an intercontinental missile who realizes the same technology could power efficient passenger aircraft, scientists discovered their interstellar designs had immediate practical applications within our own solar system. The pivot came as researchers encountered formidable obstacles specific to interstellar missions. Communication presented a significant challenge. How could a postage stamp-sized probe transmit data back to Earth across trillions of kilometers? The miniaturization requirements proved equally daunting. Compressing cameras, spectrometers, navigation systems, and power sources into a gram-scale package while ensuring they could survive decades in interstellar space introduced engineering problems without clear solutions. The physics of accelerating the light sail remained sound, but the practical implementation of a complete interstellar mission remained decades away. This realization sparked a crucial reevaluation that would make the technology relevant within our lifetimes. Researchers realized that the fundamental propulsion system designed for Alpha Centauri could be repurposed for missions within our solar system, with dramatic improvements over conventional propulsion methods. The same laser arrays and light sail designs could accelerate larger spacecraft to speeds that would revolutionize solar system exploration. This shift transformed light sail technology from a speculative moonshot into a practical near-term solution. Engineers began considering ton-scale spacecraft moving at more modest but still revolutionary velocities. These larger payloads could carry comprehensive scientific instrumentation, robust communication systems, and even sample return capabilities, all while dramatically reducing travel times compared to conventional rockets. The numbers tell the story. A journey to Mars that currently requires approximately 7 months with conventional chemical propulsion could be completed in just 3 weeks, using a laser-boosted light sail. This 89% reduction in travel time would transform Mars exploration, allowing for more frequent missions, reducing radiation exposure for potential human travelers, and enabling rapid response to discoveries or emergencies on the Martian surface. Throughout the solar system, these improvements create new possibilities. Jupiter missions that currently take years could be completed in months. the outer planets and Kuiper Belt objects would suddenly become accessible for regular scientific study. Even reaching the gravitational lensing point, 70 astronomical units from the sun, where our star's gravity focuses light from distant objects, becomes practical within a scientist's career time span rather than a multi-generational endeavor. Beyond reduced travel time, light sail technology enables responsive scientific investigation. When a comet experiences a sudden outburst or a unique interstellar object like Oumuamua passes through our system, scientific opportunity literally passes us by. Light sail technology could enable rapid response missions dispatched within days or weeks of discovery, transforming solar system science. Consider Oumuamua, the cigar-shaped interstellar visitor that passed through our solar system in 2017. By the time astronomers recognized its significance, conventional spacecraft had no hope of intercepting it. A light sail-propelled probe could have been dispatched quickly enough to rendezvous with a mysterious object, potentially answering questions that will now remain unresolved. Furthermore, focusing on solar system applications creates a practical development pathway. Interstellar missions represent an enormous leap requiring perfect performance for decades without repairs. Solar system missions, by contrast, offer progressive testing grounds with incrementally increasing distances and speeds. Engineers can validate components first on lunar missions, then Martian missions, and gradually expand outward. This incremental approach yields several advantages. First, each successful mission builds confidence and technical capability while delivering immediate scientific returns. Second, the economic case becomes more compelling since the ground-based laser infrastructure, once constructed, becomes reusable for multiple missions. Unlike conventional rockets requiring a complete new launch vehicle for each mission, the primary propulsion system remains on Earth, potentially serving hundreds of missions over its operational lifetime. Only the relatively inexpensive light sail and payload need to be manufactured for each new expedition. This reframing doesn't abandon interstellar ambitions. Rather, it creates a sustainable development path that builds toward those longer-term goals while delivering immediate benefits. The lessons learned from solar system missions directly contribute to the knowledge base required for eventual interstellar travel. The relationship works bidirectionally. Technologies initially developed for the extreme requirements of interstellar missions find less demanding but practical applications within our solar system. Material science breakthroughs for laser-resistant sails benefit solar system missions first. Miniaturization techniques developed for Starships allow more capable instrumentation on larger probes. Even scaled-down laser array technology can significantly accelerate solar system exploration. By applying interstellar technology to solar system exploration, researchers have found a way to make light sails immediately relevant rather than perpetually futuristic. This approach transforms light sails from a fascinating theoretical concept into a practical propulsion system that could launch its first missions within the coming decade. This decade, near timeline for practical missions, represents just the beginning of light sail capabilities, but the physics behind their ultimate potential harbors an astonishing possibility that a sheet of material thousands of times thinner than a human hair could be accelerated to speeds 134,000 times faster than today's fastest spacecraft. The question strikes at the heart of our interstellar ambitions. Is it genuinely possible to accelerate an object to 20% of light speed using nothing but photons? The physics of this challenge requires us to confront how motion works at relativistic speeds, velocities high enough that Einstein's special relativity becomes noticeably important. Imagine you're on a train moving near the speed of light. From your perspective inside, everything seems normal. But to someone watching from the platform, your train appears shorter. Your clock runs slower, and your mass increases. These effects, time dilation, length contraction, and mass increase, become significant at extreme speeds. While chemical rockets have taken us throughout our solar system, they operate nowhere near these velocity regimes. Conventional rockets suffer from a cruel mathematical reality. To go faster, they need more fuel, which makes them heavier, which means they need even more fuel, creating a vicious cycle. This relationship, formalized in the rocket equation, establishes diminishing returns that effectively cap conventional propulsion technologies. Even nuclear propulsion, while offering significant improvements, still faces this fundamental constraint. Enter the light sail with its elegant solution to this dilemma. Unlike conventional propulsion systems that must carry both energy source and reaction mass, a light sail leaves its energy source behind entirely. The physics underlying this approach is deceptively simple yet profound. Photons, particles of light, carry momentum despite having no mass. When photons from a powerful laser strike a reflective surface and bounce off, they transfer this momentum to the sail according to basic conservation principles. Each photon contributes a tiny push. Quintillions strike the sail continuously. These minute forces accumulate. The sail accelerates. No fuel depletes. This mechanism creates continuous thrust over extended periods, something unprecedented in spaceflight. The mathematical relationship governing this acceleration reveals why light sails hold such promise. The acceleration of a light sail is directly proportional to the laser power striking it and the sail's reflectivity, while inversely proportional to the spacecraft's mass. This creates a scaling law where a lighter craft experiences dramatically greater acceleration under the same laser power. For a gram-scale spacecraft with a perfectly reflective sail, the acceleration potential becomes extraordinary. A 10-gigawatt laser, approximately equivalent to the output of 10 large nuclear power plants, focused on a gram-scale probe, would produce continuous acceleration of multiple thousands of g-forces. Under such conditions, reaching 60,000 kilometers per second, 1/5 the speed of light, becomes achievable within minutes of laser operation. The acceleration profile follows a straightforward curve. Initially, the full power of the laser concentrates on the sail, providing maximum thrust. As the spacecraft races away from Earth, the laser beam gradually spreads out, reducing the power density reaching the sail. This spreading follows an inverse square relationship, double the distance, and the power density drops to 1/4. Despite this power reduction, the sail continues accelerating throughout the entire period it remains within the effective range of the laser. Unlike conventional rockets that must accelerate throughout their journey, a light sail requires only initial acceleration. Once the laser cuts off, the spacecraft continues at its final velocity indefinitely, without requiring additional energy input. This fire and forget approach represents a fundamental paradigm shift in how we conceptualize space propulsion. The ground-based laser array providing this acceleration would consist of millions of individual lasers working in perfect synchronization, creating a single coherent beam. The array would operate for just minutes or perhaps hours, depending on the design parameters, providing all the velocity needed for the entire interstellar journey. After acceleration, the probe would coast for years or decades until reaching its destination. What makes this approach particularly compelling is that the most expensive and power-hungry component, the laser array, remains on Earth where it can be maintained, upgraded, and reused for multiple missions. The spacecraft itself carries no propulsion system, no fuel tanks, and no bulky engines, just scientific instruments and the sail itself. The total energy needed to accelerate a gram-scale probe to 20% of light speed, approximately 125 gigawatt hours, equivalent to a small city's daily electricity use, falls within the realm of feasibility, especially when spread across a global consortium of participating nations. The laws of physics place no theoretical barrier to achieving these speeds. Unlike approaching the actual speed of light, which would require infinite energy according to relativity, reaching 20% of light speed demands significant but finite energy input. The challenge isn't one of fundamental physics, but rather of engineering implementation. At 20% of light speed, relativistic effects like time dilation exist but remain manageable. The spacecraft's clock would run only about 2% slower than Earth's during the journey. These effects become interesting scientific phenomena to measure rather than mission-ending complications. A 10-gigawatt laser concentrating its output on a light sail creates power densities that would vaporize any conventional material in microseconds. This highlights perhaps the most significant engineering challenge, developing materials that can withstand such extreme conditions without absorbing energy that would destroy them. The sail must reflect 99.99% of incident light or better, with absorption rates measured in parts per million rather than percentages. What would it mean for humanity if we could reach neighboring stars within a human lifetime? This capability would transform our understanding of our cosmic neighborhood and potentially answer one of humanity's oldest questions: are we alone in the universe? The feasibility of these missions doesn't rest on speculative physics or hope for breakthroughs in our understanding of nature. Rather, it depends on engineering challenges related to material science, laser technology, and precision manufacturing, all fields experiencing rapid advancement. The physics itself presents no roadblocks, only engineering hurdles to overcome. The material challenge, creating the impossible sail. Among those engineering hurdles, one challenge towers above all others, creating a material so impossibly thin you could stack 10,000 sheets to match the thickness of a human hair, yet strong enough to withstand forces that would instantly vaporize titanium. This material paradox represents the central obstacle in light sail development, a challenge that demands extraordinary solutions. Engineers working on light sail technology face what could be described as an impossible triangle of material requirements. The ideal material must simultaneously possess three contradictory properties: near-perfect reflectivity, negligible mass, and extraordinary resilience. Conventional materials like aluminum or gold disintegrate in microseconds when subjected to the intense power of a 100-gigawatt laser beam. Even advanced composites like carbon fiber cannot survive these extreme conditions. The material specifications are extraordinarily demanding. A functional light sail requires reflectivity exceeding 99.9% to avoid converting photons into heat rather than momentum. It must weigh mere grams per square meter while withstanding temperatures above 1,500 degrees Celsius without degradation. Think of it as requiring a miracle fabric that combines the weightlessness of a soap bubble, the reflectivity of a perfect mirror, and the heat resistance of space shuttle tiles, all in a single material. The physics creates a fundamental contradiction. We need something substantial enough to reflect photons and maintain structural integrity, yet so lightweight that those same photons can propel it to significant fractions of light speed. Conventional engineering wisdom suggests these requirements cannot coexist in a single material. Crystalline silicon nitride has emerged as a leading candidate material, the same substance being explored at Caltech's nanoscience facilities. Its remarkable properties allow it to maintain structural integrity even when fabricated into films just tens of nanometers thick. Silicon nitride offers exceptional thermal stability, withstanding temperatures that would melt most alternative materials. Its crystalline structure can be precisely engineered at the atomic level to control exactly how it interacts with light. Other promising approaches include synthetic, diamond films, and metamaterials. Diamond films combine extraordinary strength with low mass and superior heat dissipation, while metamaterials engineered at the nanoscale can be designed with specific optical properties to enhance reflection while minimizing absorption. Both technologies show potential despite manufacturing challenges. The mechanical stresses during acceleration compound these material challenges. These ultra-thin membranes must withstand hundreds or thousands of G-forces that would instantly tear apart conventional materials. The sail experiences tremendous strain as photons transfer their momentum, requiring exceptional tensile strength despite gossamer thinness. Material scientists are developing structural designs that distribute these forces evenly across the sail, preventing concentration points that could lead to catastrophic failure. Heat management is equally critical. Even with reflectivity exceeding 99.9%, the minute fraction of absorbed energy becomes significant with multi-gigawatt laser systems. Without convection cooling in space's vacuum, the sail must rely solely on radiation to shed excess heat. Advanced cooling mechanisms include structured radiators that efficiently emit thermal energy away from the sail. Some designs incorporate specialized coatings that enhance thermal radiation at specific wavelengths. Another approach involves designing the sail with microscopic perforations that reduce mass while providing paths for heat transfer throughout the structure. Nanofabrication techniques are proving essential to solving these material challenges. Methods like atomic layer deposition allow engineers to build materials one atomic layer at a time, controlling properties with unprecedented precision. These techniques create atomically perfect surfaces that maximize reflection while minimizing defects. The ideal light sail material must possess specific properties to withstand the extreme conditions of space travel, notes a report from the Breakthrough Starshot materials team. These include high reflectivity to maximize the force from photons, a low mass per unit area to enable rapid acceleration, and exceptional heat resistance to endure the intense energy from a laser beam. The manufacturing precision required is staggering. Surface irregularities must be controlled at the nanometer scale, equivalent to ensuring that a football field doesn't vary in height by more than the width of a human hair. Any imperfection could create hotspots where the material absorbs rather than reflects light, potentially leading to cascading failure. Despite these formidable challenges, encouraging progress continues. Researchers have demonstrated materials with reflectivity exceeding 99.95% in laboratory settings. Advanced materials like silicon nitride have been fabricated at thicknesses below 50 nanometers while maintaining structural integrity. These materials can withstand laser intensities that would destroy conventional alternatives, suggesting that the barriers to light sail technology are substantial but not insurmountable. Recent breakthroughs in material science have transformed theoretical concepts into engineering problems with plausible solutions. The development of atomically precise manufacturing techniques, coupled with our growing understanding of nanoscale material properties, is creating a technological foundation for viable light sails. These advances don't require new physics, just the continued refinement of existing material science capabilities. The challenges facing light sail materials illuminate a broader point about space technology development. The extreme requirements of space exploration often drive material science innovation that eventually benefits terrestrial applications. The atomically precise materials being developed for light sails could eventually lead to advances in fields ranging from electronics to medicine, demonstrating how pushing technological boundaries in one domain often yields unexpected benefits elsewhere. Payload possibilities, from starships to science labs. The same material innovations enabling light sails have sparked a parallel revolution in miniaturization. Imagine fitting an entire interstellar laboratory onto something smaller than your thumbnail. A spacecraft so tiny you could mail it with a single stamp, yet sophisticated enough to investigate an alien solar system 20 trillion miles away. This scenario isn't science fiction. The emerging field of gram-scale spacecraft represents perhaps the most radical reimagining of space exploration since the space age began. These starships, thin as a credit card and barely wider than a postage stamp, challenge our conventional understanding of what constitutes a functional spacecraft. This miniaturization is a necessary response to the unforgiving physics of interstellar flight. Mass and acceleration form the central tension in light sail mission design. Each additional gram dramatically reduces maximum achievable speed. For interstellar missions targeting 20% light speed, a 1 gram probe might reach Alpha Centauri in 20 years, while adding just 10 grams could extend the journey to over a century. Engineers must ruthlessly minimize mass to just a few grams total. Within such extreme constraints, conventional instruments become impossible. Standard cameras weighing hundreds of grams or spectrometers weighing kilograms have no place on starships. The solution lies in microelectromechanical systems, MEMS, where sensors and actuators are fabricated using techniques developed for computer chips. MEMS technology creates accelerometers, gyroscopes, and pressure sensors at microscopic scales, components critical for navigation and data collection. A MEMS-based camera might combine an optical sensor smaller than a fingernail with microscopic silicon-etched lenses weighing milligrams rather than grams. A gram-scale starship could carry several miniaturized instruments. Semiconductor cameras just millimeters across might capture the first close-up images of Proxima Centauri B's surface features, perhaps revealing continents, oceans, or cloud patterns. Silicon chip spectrometers could analyze light reflected from exoplanets to detect water vapor, methane, or oxygen in alien atmospheres. Particle detectors no larger than a rice grain could map the interstellar medium, measuring cosmic rays and dust concentration between star systems. Power generation presents another challenge. Microscopic solar cells could harness energy from the driving laser itself. Once beyond laser range, tiny spacecraft might generate minimal power from starlight, or carry miniature radioisotope sources barely larger than a pinhead. Communication systems must function across vast distances with minimal mass. A gram-scale probe might repurpose its entire light sail as an antenna after acceleration ends. Laser communication systems weighing just grams could potentially transmit data across interstellar distances, though at extremely limited rates. The mass budget dictates hard choices about which instruments to include. Every milligram must be justified, shaping the scientific questions that can be addressed. While a gram-scale probe couldn't conduct comprehensive studies of an exoplanet, it could detect biosignatures in an atmosphere or measure magnetic field strength, potentially revealing whether a distant world harbors life or a molten core. Solar system missions present a more forgiving context. Without requiring relativistic speeds, light sails for planetary exploration could carry larger payloads, ranging from 5 to 100 kilograms. At this scale, more conventional instrument suites become possible. High-resolution cameras, comprehensive spectrometers, and even sample collection mechanisms. A 20-kilogram light sail probe to Mars could carry sensors capable of resolving surface features down to centimeters, analyzing methane plumes in real time as they emerge. The reduced travel time, potentially just weeks instead of months, would enable rapid response science missions to investigate transient phenomena. A 50-kilogram mission to Europa could include ice-penetrating instruments to study the subsurface ocean, while a similar mission to Enceladus could analyze its geysers composition, potentially detecting organic molecules or even microbial biosignatures. For these larger solar system missions, power generation becomes more manageable, with conventional solar panels providing adequate electricity. Communication systems can utilize traditional radio frequencies, achieving much higher data rates than their interstellar counterparts. Both classes of light sail missions share common engineering challenges. The instruments must withstand extraordinary acceleration forces during laser propulsion. These forces could reach hundreds or thousands of Gs, requiring entirely new approaches to instrument design, emphasizing solid-state components with no moving parts. The scientific potential extends beyond replicating existing capabilities at higher speeds. The constraints of light sail missions drive innovation in instrument design. Microfabrication techniques developed for Starships are already finding applications in conventional spacecraft. The questions we might answer are transformative. Does Proxima b have an atmosphere containing oxygen? Are there seasonal changes on distant worlds? For solar system targets, what organic compounds emerge from Enceladus plumes? How do Martian dust storms form in their earliest stages? The ability to reach destinations quickly transforms what scientific questions we can meaningfully ask. Technologies developed for Starships have applications beyond space exploration, advancing medical devices, environmental monitoring, and advanced manufacturing. The push to create ever smaller scientific instruments is accelerating broader technological trends toward miniaturization and integration. Breakthrough Starshot, engineering an interstellar mission. Beyond theoretical discussions of light sail capabilities lies an audacious engineering project already underway. While scientists refine nanoscale prototypes in laboratories, the Breakthrough Starshot initiative is simultaneously developing the infrastructure needed to transform interstellar travel from science fiction into reality within our lifetime. When Stephen Hawking and Yuri Milner unveiled the Breakthrough Starshot initiative in 2016, their $100 million commitment signaled genuine determination to solve the engineering challenges of interstellar travel. This funding launched a coordinated effort to develop all systems necessary for humanity's first mission beyond our solar system. The initiative's approach diverges radically from conventional space mission design. Rather than focusing on a single spacecraft, the plan calls for launching thousands of tiny probes toward Alpha Centauri. This redundancy is strategically essential given the unprecedented challenges of interstellar space. With multiple starships traveling together, the mission could continue, even if individual probes fail during the 2-decade journey. Breakthrough Starshot's technical architecture consists of three interdependent systems: a massive ground-based laser array spanning approximately 10 square kilometers to generate propulsive energy meter-scale ultra-thin light sails made from advanced materials capable of withstanding intense laser-powered gram scale. Starship spacecraft containing miniaturized scientific instruments. We are human beings, and our reach extends to the sus. We are human beings, and our reach extends to the sus. We are human beings, and our reach extends to the SES initiative. For the first time in human history, we can do more than just gaze at the stars. We can actually reach them. The colossal scale of the laser array represents the most ambitious engineering aspect. To accelerate spacecraft to 20% of light speed, the system must generate approximately 10 gigawatts of concentrated power, equivalent to several nuclear power plants. The array requires perfect synchronization across millions of individual lasers, sophisticated adaptive optics to counteract atmospheric distortion, precise targeting systems, and robust thermal management solutions. In stark contrast to this massive Earth-based infrastructure stand the tiny starships themselves. Each probe must contain navigation systems, computing capabilities, power generation, and scientific instruments, all within a package weighing just a few grams. The spacecraft design must withstand thousands of G-forces during acceleration, far beyond what conventional satellites endure. This juxtaposition of scales, from the kilometer-wide laser array to gram-weight spacecraft, exemplifies the initiative's innovative approach to solving interstellar travel's fundamental challenges. The mission architecture proposes launching thousands of starships in formation. This swarm approach creates redundancy while allowing for distributed data collection across the Alpha Centauri system. Some probes could be sacrificed for high-risk observations while others maintain core mission objectives. At 20% of light speed, these spacecraft would reach Alpha Centauri in approximately 20 years, a fraction of a human lifetime. This velocity represents an extraordinary leap from our current interplanetary missions, which typically travel at less than 0.1% of light speed. The Parker Solar Probe, currently our fastest spacecraft, would take thousands of years to reach even the nearest star. The brevity of the actual encounter presents unique challenges. At such tremendous velocities, the starships would have only seconds to capture data as they race through the Alpha Centauri system. The instruments must automatically trigger at precisely the right moment, capturing as much information as possible during their fleeting visit. The onboard systems must correctly identify observation targets, adjust instrument settings, and collect data, all autonomously. Unlike missions within our solar system, the 4.3 light-year distance means any instructions would take years to arrive. The entire scientific mission must be pre-programmed or governed by sophisticated artificial intelligence. Communication presents another formidable challenge. The Breakthrough Starshot team is exploring innovative solutions, including repurposing the light sail itself as a transmitter or using the sun's gravitational lens as a natural amplifier. Even with these approaches, data transmission rates would likely be measured in bits per second, requiring careful prioritization of information sent back to Earth. The initiative follows an ambitious yet methodical timeline. Throughout the 2020s, researchers are focusing on proving key technologies. The 2030s would likely see prototype systems and possibly test missions within our solar system. Under optimal conditions, the first interstellar launch might occur in the 2040s, with data returning from Alpha Centauri around 2070. This progression makes Breakthrough Starshot a defined engineering roadmap with specific technical milestones. While challenges remain formidable, none appear to violate fundamental physical laws. The questions now center on engineering implementation rather than theoretical possibility. The impact of even partial success would transform our understanding of neighboring star systems. Direct measurements of exoplanets, interstellar medium composition, and potentially even biosignatures would answer questions that have intrigued humanity for centuries. What's remarkable about Breakthrough Starshot is how it leverages existing technological trends rather than requiring fundamentally new physics. The initiative builds upon advances in material science, laser technology, miniaturization, and computing, fields already progressing rapidly for commercial and scientific reasons. When considered alongside the challenges of conventional propulsion systems, the light sail approach begins to appear potentially practical. Traditional rocket systems face fundamental limitations when scaled to interstellar distances, making breakthrough technologies necessary regardless of which approach humanity pursues. Traditional rocket systems don't just hit their limits at interstellar distances, they're already severely constrained within our own cosmic backyard. What if the journey to Mars could take just 3 weeks instead of 7 months? The rocket equation, a seemingly simple mathematical relationship, explains both why we've been stuck with slow interplanetary travel and how light sails might finally break us free from this constraint. The fundamental limitation of conventional rockets lies in a mathematical reality that aerospace engineers have grappled with since the dawn of space exploration. Think of a rocket like a car that must carry not only its passengers, but also every drop of fuel needed for the entire journey, and the car itself gets heavier with each gallon added. As a rocket burns fuel, it must push not only its payload, but also all of its remaining propellant. This creates a vicious cycle. Achieving higher speeds requires more fuel, but more fuel means more mass, which requires even more fuel to accelerate. This exponential relationship effectively places a ceiling on the practical velocity any traditional rocket can achieve. Consider a typical mission to Mars. Even with our most advanced chemical propulsion systems, spacecraft require approximately 7 months to reach the red planet. This extended journey presents numerous challenges, from radiation exposure to psychological strain on potential human crews, plus the substantial supplies needed for such lengthy voyages. These limitations represent a fundamental constraint of physics that no amount of conventional rocket optimization can overcome. The rocket equation's tyranny becomes more pronounced for missions beyond Mars. Jupiter missions typically require years of travel time, while probes to the outer planets need gravity assists and complex multi-year trajectories to reach their destinations. This slow pace severely restricts our scientific understanding of the solar system and limits our ability to respond quickly to interesting phenomena. Light sails offer a radical alternative by sidestepping the rocket equation entirely. Rather than carrying propellant, they harness external energy, either from sunlight or more powerfully from ground-based lasers. This approach fundamentally changes the mathematics of space travel. With no need to carry fuel, there's no cascading penalty for additional acceleration. Instead, light sails can continuously accelerate as long as they remain within range of their energy source, potentially reaching velocities that conventional rockets could never practically achieve. The contrast becomes striking when examining specific mission scenarios. A laser-boosted light sail could potentially complete a Mars journey in just 3 weeks, reducing travel time by nearly 90%. This represents a transformative capability that would revolutionize planetary exploration and potentially enable human exploration with dramatically reduced life support requirements. What makes this approach particularly compelling is that it addresses multiple constraints simultaneously. By eliminating the need to carry propellant, light sails dramatically reduce spacecraft launch mass. This translates directly to lower launch costs, as getting each kilogram into orbit remains one of the most expensive aspects of space exploration. Even with the substantial investment required to build a ground-based laser array, the economics become increasingly favorable when amortized across multiple missions. The economic advantages extend beyond reducing launch mass. Conventional deep space missions require complicated, heavy, and expensive propulsion systems. By contrast, light sail missions place the most complex component, the propulsion system itself, on Earth. The ground-based laser array would never leave our planet, allowing for easier maintenance, upgrades, and reuse across dozens or even hundreds of different missions. This Earth-based engine approach creates additional economic efficiencies through specialization. The laser array can be continuously improved, maintained by specialized technicians, and upgraded with new technology. Power generation can utilize existing terrestrial infrastructure rather than the severely constrained power sources available in space. These advantages make light sail missions potentially more cost-effective than conventional approaches, particularly for repeated journeys. Another significant advantage comes when considering the challenge of deceleration. Conventional rockets must reserve approximately half their fuel budget for slowing down upon reaching their destination. Light sails can utilize alternative deceleration methods that don't require carrying additional propellant, such as solar braking techniques or stellar braking for interstellar missions. Light sail propulsion also represents a more sustainable approach to space exploration. Conventional chemical rockets rely on toxic propellants that pose environmental risks. Nuclear propulsion, while offering improved performance, raises concerns about radioactive materials. Light sails eliminate these environmental hazards as they rely solely on photon momentum for propulsion. For certain types of missions, particularly those requiring rapid response to transient phenomena, light sails offer capabilities that conventional propulsion cannot match. A laser-boosted light sail could potentially reach targets like a newly discovered comet in a fraction of the time, enabling previously impossible rapid response science. The comparative advantages become particularly compelling when considering interstellar exploration. Conventional propulsion systems would require centuries to reach even the nearest stars, while nuclear propulsion concepts might reduce these timeframes to decades. They remain theoretical. Light sails, with their potential to reach significant fractions of light speed, represent perhaps our most viable near-term approach to interstellar exploration. It's important to recognize that light sails aren't superior for all mission profiles. They face challenges with heavy payloads, precise maneuvering, and operations far from their energy source. The optimal approach will likely involve a mix of propulsion technologies tailored to specific mission requirements. But how might our understanding of the cosmos transform if we could reach Mars in weeks rather than months, or nearby stars in decades rather than millennia? The remaining hurdles: navigation, survival, and communication. Beyond the extraordinary challenges of propulsion and material science, a fundamental problem emerges when traveling at relativistic speeds. Navigation becomes an entirely different game. While our spacecraft might achieve impressive velocities approaching 20% of light speed, this creates a dangerous paradox. The faster we go, the more vulnerable we become to the smallest particles in space. At such velocities, navigating through space becomes like threading a needle in a cosmic hailstorm. A microscopic speck of dust that would harmlessly bounce off a conventional satellite transforms into a devastating projectile. The kinetic energy involved makes even particles the size of a micron potentially catastrophic. This follows directly from physics. When traveling at hundreds of thousands of kilometers per second, your spacecraft lacks the time to detect and avoid obstacles. By the time sensors register a potential collision, the impact has already occurred. This navigation challenge represents perhaps the most significant hurdle for light sail missions. Traditional avoidance systems cannot react quickly enough at these speeds. Engineers are developing multi-layered approaches, beginning with pre-mission mapping of the spacecraft's trajectory using astronomical data to chart paths through minimal debris. Yet space remains dynamic. Objects move, and our maps remain incomplete. A more robust solution combines distributed sensor systems with autonomous collision avoidance. Imagine a formation of light sails traveling together, with forward scouts positioned to detect hazards and relay data to the main spacecraft. This architecture provides redundant monitoring capabilities, while specialized hardware processes sensor data and executes evasive maneuvers almost instantaneously. The system makes split-second decisions without human input, as communication delays render Earth-based control impossible during critical moments. Even with advanced navigation systems, impacts remain inevitable at relativistic speeds. This reality drives research toward innovative approaches to spacecraft survivability. One promising direction involves self-healing materials capable of autonomously repairing damage. The Space Entanglement and Annealing Quantum Experiment, SEEK, on the International Space Station demonstrates this concept, testing a novel method to transmit quantum data, while validating technology to self-heal its sensitive detectors against radiation damage using laser annealing. Metal halide perovskites exemplify these self-healing properties. These materials, abundant in Earth's crust, show remarkable recovery capabilities from radiation damage. Research indicates that high-energy protons can heal the damage caused by low-energy protons, allowing the device to recover and continue doing its job. This property, absent in conventional semiconductors, provides a crucial advantage in the harsh radiation environment of space. Distributed spacecraft architectures enhance survivability further. Rather than designing a single monolithic craft, engineers develop modular systems where functionality spreads across multiple components. If one section suffers damage, others compensate, ensuring mission continuity. These redundant systems prove particularly valuable for interstellar missions where repair is impossible and mission durations span decades. Communication presents that third major challenge, particularly beyond our solar system. Traditional radio communication becomes increasingly difficult across interstellar distances, with signal strength diminishing according to the inverse square law, much like how a flashlight beam grows dimmer the farther away you stand. A transmission strong near Earth becomes virtually undetectable after traveling several light years. Power limitations compound this challenge. A gram-scale Starship carries minimal power generation capability, yet must transmit data across trillions of kilometers. One innovative solution repurposes the light sail itself as a giant antenna after the acceleration phase. The sail's large surface area can potentially amplify weak signals, improving successful data transmission. Optical communication using powerful, precisely aimed lasers offers another approach. These create extremely narrow beams to maximize signal strength over vast distances, while data rates remain limited by available power and receiver sensitivity. Even modest transmission capabilities provide valuable scientific returns from interstellar space. The quantum communication technologies being tested by SEEK could transform these capabilities by developing foundations for a scalable quantum information network. These experimental technologies hint at future systems able to transmit data more efficiently across cosmic distances. Navigation, survival, and communication form an interconnected triad where improvements in one area contribute to solutions in others. Distributed spacecraft architectures enhance both navigation capabilities and survivability. Advances in material science contribute to structural integrity and communication capabilities through multifunctional components. The development of self-healing materials for surviving microparticle impacts also enables more resilient communication equipment. Engineers approach these challenges pragmatically, recognizing that perfect solutions aren't necessary, only those good enough for successful missions. A mission launching thousands of gram-scale probes might accept many losses to impacts, provided enough survive to complete objectives. None of these engineering challenges appear fundamentally insurmountable. Unlike propulsion, which required breakthroughs in physics, these hurdles involve creative applications of existing technology pushed to its limits. The physics behind navigation, survival, and communication is well understood. Innovation lies in implementation under extreme constraints. Before any interstellar mission launches, engineers will deploy prototype spacecraft within our solar system, demonstrating technologies in progressively challenging environments. Missions to Mars or Jupiter using light sail propulsion would validate systems under less extreme conditions than interstellar space. The solutions being developed often have applications beyond space exploration. Self-healing materials could revolutionize aircraft safety and infrastructure longevity. Distributed sensing networks might improve environmental monitoring on Earth. Quantum communication technologies could transform secure data transmission across global networks. This technological cross-pollination provides additional motivation for solving these complex challenges. We're standing at the threshold of an extraordinary philosophical frontier. As interstellar travel moves from science fiction to scientific possibility, we face profound questions about humanity's cosmic purpose. What responsibilities come with extending our presence to other star systems? How might contact with extraterrestrial life reshape our understanding of consciousness and intelligence? These are immediate philosophical concerns. The technological trajectory suggests the first humans to witness an interstellar mission launch may already walk among us. This transformation requires us to consider what we might discover and who we hope to become. What part will you play in humanity's greatest journey beyond our solar cradle?